Hello, Mr. Kitchen, Cobleskill, Richmondville High School Physics. Today we take a look at potential energies. Energies plural because there are two kinds that we're going to take a look at in the high school course. The first one is gravitational potential energy, and that is the energy that something has due to its position in a gravitational field. Now, we said that energy is basically due to the work that you do on that object. So the force of gravity is a vertical force, and therefore we have to use the vertical distance. So we're going to be using the height in the gravitational field. A couple symbols that we use for gravitational potential energy, and you'll see me use both in class. Classically, we use PE sub G for potential energy of gravity, but the Regents reference table uses delta PE because the change in gravitational potential energy is due to height. There's always going to be a change involved, and so they just use the delta PE instead. Now, the formula for gravitational potential energy is delta PE is the gravitational force multiplied by the vertical distance, so we have mg delta H. And if you take a look at this, we're really calculating the work done in order to lift something. This is the gravitational force right here, mg, and this is the vertical distance, or the distance in the direction of that force. Here's a quick example using gravitational potential energy. Let's say we have an 10 kilogram block, and there's an inclined plane at 30 degrees. The height of this inclined plane is 1.8 meters. So our delta PE is mg delta H. So we could say delta PE is the product of 10 kilograms. We've got to multiply by the acceleration of gravity, 9.81 meters per second squared. There's our 98.1 newtons of force. We use 98.1 newtons of force in the vertical direction. The vertical height is 1.80 meters. When I multiply those together, I got 177. But to two significant digits, we're going to say 180 joules. Now, the other type of potential energy that we talk about is elastic potential energy. And all these potential energies are due to work. This is the work done to compress or stretch a spring. You know, we can think about taking a spring and squeezing it together, or taking a spring and stretching it apart. I quoted when I said spring, though, because this applies to anything that acts like a spring as well. If you compress air molecules, they behave in a springy way. If you stretch a garbage bag, it behaves in a springy way, and so does a piece of steel. So we have PE sub S, the symbol that we're going to use, potential energy of a spring, and that's 1/2 kx squared. K we've seen before, it's the spring constant. We saw that in Hooke's law, and that's measured in newtons per meter. And X is the symbol we use for the change in length, and we measure that from the equilibrium position. So we'll start off with, or we'll end up with, a little example of elastic potential energy. Let's say we have spring. This is the same spring before and after. Originally, the spring has a length of 0.4 meters, and it has a spring constant of 28 newtons per meter throughout. We apply, well, it says 1 kilogram there. I know it's hard to read. But we hang a kilogram on the end of it. Of course, that's 9.81 newtons of force, and the spring stretches to a total length of 0.7 meters. Now, we start out with potential energy of the spring is 1/2 kx squared, and I'm just checking to see if people are listening to the audio here, so I'm just going to tell you what to write on the next two lines, and I'll check it in your notes. The potential energy of the spring will be equal to 1/2 times, and then put a set of parens, the value for K, just put 28 newtons per meter in there. And then X is the change in length between 0.4 and 0.7. So it's 1/2 times 28 times 0.3 meters quantity squared. And when we multiply that all together, the last line you can put potential energy of the spring is 1.26 joules. We'll pick up with other examples of this, and I'll show you the derivations from the work formula in class.